Welcome back to Honors Calculus. In this video, we're going to be talking about the tangent line problem. And the idea of a tangent line is the heart of the study of calculus, at least the way it is traditionally presented. When I'm talking about tangent lines, I want you to think about an arbitrary curve in the coordinate plane. I'm not going to bother drawing the coordinate axes because I don't care where this is. And if there's one thing that you have learned so far about graphing the equations of functions, is that when the function is a linear function, it is incredibly easy to work with. And whenever you have anything other than a linear function, you really wish that you had a linear function instead. And that's the goal of the tangent line problem. If we find a line, let's try drawing that a little bit better. If we find a line which is tangent to the curve at a point, it touches the curve at one point and nowhere else. And then we go and we zoom in just on the place where that touches. If you zoom in far enough, you can't tell the difference between the curve and the line. When calculus first came into importance, this in and of itself was an incredibly important skill. Because by finding a tangent line, you can use that to approximate the value of a function at a ridiculously ugly decimal place value. Today, we have computers that will do the work for us. We don't have to resort to those kinds of tactics. I'm still going to show you how that works because it's a nice way of making sense of what the tangent line does. And there's going to be so much more that the tangent line will be able to do for us as we move forward. All right, so let me go ahead and get my head out of the way, and let's take a look at what I mean here. The line tangent to the curve y equals f of x at the point where x equals c is a line that passes through the point c, f of c, and the next consecutive point on the curve. So if we have our c, and f of c, then at some point, infinitesimally close, there is another point right there. Let's call the distance between those 2 points along the x direction delta x. And, excuse me. Now, a curve represents a continuum. There are infinitely many points on any curve. And given any curve, and given any 2 points, or even just given the x-axis and given any 2 points on the x-axis, there is always another point that falls between them. So the idea of a next consecutive point doesn't really seem to work. But we've developed this really interesting structure. We know we have a point C and f of c. And we can look at another point, c plus delta x, f of c plus delta x. What happens to this point, c plus delta f, f of c plus delta x, as delta x goes to 0? Well, it converges into the other point. And yet, because of the definition of the limit, remember, the epsilon delta definition of the limit says that 0 is less than the difference between the point, or the variable and the point, is less than delta. So delta x in this case has to be somewhere between 0 and delta. Not equal to 0, not equal to delta, but somewhere in between. So we want to get delta x as close to 0 as possible without actually getting to 0. And if you squint and tilt your head just right, you can convince yourself that that's the same thing as saying that we want the next consecutive point after c plus delta x, where delta x is nearly 0, indistinguishably different from 0, but not actually 0. And so that's what we're looking at here. If we want to have a point f of c plus delta x, I'm sorry, c plus delta x, f of c plus delta x, well, we can take the limit as delta x goes to 0, and we can calculate the slope of the line through these 2 points. F of c plus delta x minus f of c all over c plus delta x minus c. Let's make that delta actually look like a delta. Notice in the denominator, that the plus c and the minus c will cancel each other out. Giving us this expression. And since we're taking the limit, instead of thinking about m as delta y over delta x, change in y over change in x that you commonly think of, we're going to call this thing dy over dx. We switch from the delta to the d to say this is the instantaneous slope instead of the average slope. To show you what I mean here, let's jump over to a graph in Desmos. So here I have what's called my secant line graph. You can see the title. I have a mystery function y equals f of x that's graphed here in, I guess that's blue. I've got a couple of points. My point of interest, c f of c, and then Desmos doesn't really handle delta x well, so I've labeled this as h instead of delta x, but it means the same thing. And then I've graphed the equation of the line that has the slope between those 2 points. And if you scroll over, you can see that it's got the x and y coordinates of those points. And I have a slider here which controls the value of h, my delta x stand-in. And what you can see is that as it stands originally, the line is kind of similar to the function. At these points, you can see that it has a lot of similarities. But if I let it go ahead and come in closer, you can see that it becomes closer and closer and closer to the function in question. All right, let's zoom in on that point, or on the point between these 2 dots a little bit. And you can see that the process just keeps going. As we get closer and closer, we come to the point where you can't hardly tell the difference between the two functions. But if we zoom in a bit further, you can start to see that they are different things. And so we get closer and closer still until we can find a point where we zoom in far enough. And no matter how far you zoom in, you can't really tell the difference between them anymore. All right, that's what we're looking for when we're talking about the tangent line. We may have to zoom in incredibly far to get there, but there should be something we can do. All right, let's head back over to my notes. And to see that this makes sense, let's take a look at a particular example. Let's find the equation of the line tangent to the curve defined by the equation y equals x squared when x is equal to 1. So in order to do this, we could start off by graphing. You know what the function y equals x squared looks like. As functions go, it's fairly straightforward. You know that the point here, when x is equal to 1, we can quickly calculate that y of 1 is also equal to 1. So we're going through the point 1, 1, and you can kind of get a visual for what that tangent line should look like. And so there is our goal. We set c equal to 1, we set f of c equal to 1, and we start plugging things in. We're taking the limit as delta x goes to 0 of f of c plus delta x. So that's going to be 1 plus delta x squared minus f of 1, which is just 1, all divided by delta x. All right, just plugging in c equals 1 and f of x equals x squared to see what we get out of this. We can simplify this expression, 1 plus delta x, the whole thing squared, is 1 squared, which is 1, plus 2 times 1 times delta x, which is just 2 delta x, plus delta x squared minus 1, all over delta x. Notice we have a 1 and a minus 1 in the numerator. So this thing turns into 2 delta x plus delta x squared all over delta x. And if you try plugging in that delta x is equal to 0, you get 0 over 0, which is an indeterminate form. As indeterminate forms go, this one is not too bad. We should be able to divide off that delta x, and in fact, we can do that pretty readily. Just divide each term by term. So this is equal to the limit as delta x goes to 0 of 2 delta x divided by delta x is just 2. Delta x squared divided by delta x is just delta x. And then this goes to 2 plus 0, which is 2. So our slope m, or our dy dx, for this particular curve is just 2. With that, our problem has simplified. The question is now asking us to write the equation of the line through the point 1, 1 with a slope 2. And that's really easy to do. Y minus the y coordinate, which is 1, is equal to the slope, which is 2, times the quantity x minus the x coordinate, which is 1. And if we clean up a little bit, we get that y is equal to 2x minus 1. If I jump back over to Desmos really quickly, I can graph the function that we were studying, which is just y equals x squared. And I can graph the tangent line that we came up with, y equals 2x minus 1. And for the sake of convenience, I can plot in the point that we cared about, 1, 1. And then playing the same trick that I played before. I can use the zoom in button here, or you can just use the scroll wheel on your mouse if you're on a desktop computer. I'm hovering my mouse over the point in question. Sometimes it helps to actually click on the point in question, and I'm just zooming in. And my goal is to keep zooming in until I get far enough that the curve y equals x squared and the line y equals 2x minus 1 are indistinguishable from each other. Now there's certainly a window here where that's the case, but you can see that they branch off relatively quickly. So let's zoom in a little bit further. All right. I think at this point, I can't really tell the difference. Maybe just barely at the top and bottom of the screen. So let's zoom in one more notch. Yeah, that looks like a good place to be. All right, I'm very far away from the coordinate axes, so I have to rely on the fact that Desmos gives us scaling that filters in here. But you can see here, 0.98 up to about 1.02 is the range of x values that we had to zoom into, and something about 0.96 up to about 1.03 or somewhere thereabouts is the y values that we've zoomed into. Somewhere thereabouts. I'm not being all that precise. Again, if you really squint down at the bottom of the screen, you can see where they start to separate. At the top, maybe someone else can, but I can't tell the difference. But we can see that the two curves are indistinguishable from each other once you zoom in that far. That's what the tangent line approximation is all about. That's what we've been looking for here, and we're very happy to have found it. When I started in on this lesson, I said that the reason that this was first so powerful was that it gave a tool for approximations. And so with this relatively simple function, we have a tool for dealing with squares and square roots, as long as we are somewhere near the point 1, 1. We use the graph to figure out exactly how near we have to be to get a reasonably correct value, but that general idea of somewhere near the point 1, 1 is what we're really thinking about. And so with just this result, if I wanted to approximate the square root of 1.9, I'm sorry, not 1 point, 0.9725 by hand, I would hate my life. But we're looking for a value y equals x squared. That's the same thing as saying that x is equal to the square root of y. So if we say that y is 0.9725, then x is the square root of 0.9725. And we can use our tangent line approximation to get something close to that value. So 0.9725 is approximately 2 times the square root of 0.9725 minus 1. Add 1 to both sides of the equation. 1.9725 is approximately 2 times the square root of 0.9725. Right? So that means that 2 times 1.9725, which is not exactly easy, but it's also not that hard. Sorry, not 2 times, 1/2 of. So we want to take 2 goes into 1.9725. 2 fits into 1, well, it doesn't. 2 fits into 19 9 times. 9 times 2 is 18. Subtract that off, you get 1. Drop down to 7. 2 fits into 7 8 times. 2 times 8 is 16. Subtract that off, you get 1. Drop down to 2. 2 fits into 12 6 times. 2 fits into 5 twice. And I get that the square root of 0.9725 is approximately 0.98625. As recently as the 1980s, that would have been the end of the story. We needed to calculate a square root, and we used this approximation to do so. But of course, today we live in an age of calculators, so I can go ahead and ask my calculator, what is the square root of 0.9725? And my calculator tells me it is 0.986154. That is incredibly close. One of the things that we often talk about, and we'll look at a little bit more carefully later on in this course, is what's called propagation of error. Given an error in how you calculated your original value, how does that turn into an error in the resulting value? And one of the ways we measure that is by how many non-zero digits there are in the number. 0.9725 is measured to the nearest 10,000th. 0.986, well, we would round that up to 0.9863, or the result that came in my calculator, 0.9862, would be how I would round it to the same number of digits as what we had in the first place. And we're off by 1. I'll count that as a success. All right. So again, this process of using a tangent line in order to approximate the value of a function has its uses. We're not going to get into any of the more esoteric uses, but for those of you who are continuing onward to study physics, engineering, even finance and economics, there are a lot of places where looking at this a little bit more generally is going to open up a tool for dealing with situations you couldn't otherwise. Right, so calculating a value like this, not necessarily the value of the tangent line approximation, but if we can replace a difficult to work with function, like a squaring function or a square root function or a trig function or something more complicated than that even, with a linear function, with a line, and then do more algebra from there, how much easier is our life going to be? Right? I unfortunately don't have enough time to show you any examples of how that works, but it is something I want you to keep in mind as you're looking through this. And honestly, the rest of everything we do in this course is going to be based around that idea. But for right now, let me get my head out of the way so that I can give you a similar problem to try. And when I say similar problem, I mean very similar problem. I would like you to find the equation of the line tangent to the function y equals x squared at the point where x is equal to 3, which is going to be surprisingly different from the one that we just found. But then continue the process that I showed you. Graph the function and your tangent line using Desmos or the tool of your choice, and then zoom in until you can find an interval where the tangent line is a good approximation. All right? See what you can do with that problem, and I'll see you in the next video.